Thank you again for watching one of my videos. This one is about building a project using the TI Launch Pad Launch XL F28377S. First then, we should start by meeting this launch pad. These are actual images of my Launch XL, or the Fino Launch Pad as I like to call it. I use the box as the case for the board. This is why the box looks beaten up. Here it is out of the box. The flash drive is to relate to its actual size. It comes with a USB cable to connect it directly to a PC. The Delfino Launchpad is a development board for the TI microcontroller F28377S. The board exposes many of its signals for direct measurement and observation through 4 40-pin connectors. These connectors are also for direct connection with TI booster packs, such as those indicated in this brochure, the Motor Driver Booster Pack and the Digital Power Booster Pack. I have a Digital Power Booster Pack that I'm planning to use to control the output voltage of a DC to DC converter with a real-time discrete PID controller. Here we can read the good things of the launch pad. The F28377S is a powerful low-power microcontroller. It has a 200 MHz CPU, a 200 MHz coprocessor that assists with floating point operations, 1 MB of flash, 164 KB of RAM, 15 channels for PWM, 14 12-bit ADC channels, and several kinds of serial communications peripherals, among other things. In other words, this little beast is a serious microcontroller for serious businesses, such as control and signal processing applications. The board comes with a JTAG emulator for programming and debugging. It comes also with user LEDs, or LEDs as I like to call them. We will make these LEDs blink in the application described in this video. Last but not least, we have the software tools that TI provides with the purchase of the launch pad. This software will expedite the development time since it comes with libraries, drivers, and examples. It's worth noting that the reference manual of the F28377S MCU contains more than 2,000 pages. Creating the APIs that programs and controls the hardware of this device will be gargantuan. TI documentation is abundant but scattered, and sometimes outdated. To create this project, we are going to use 2 documents. The first document is the F28377S User's Guide. This User's Guide release, I believe, is the latest and was made in May 2017. If we move to page 15, we find instructions on how to create the Blink project. This is a good reference, but I have modified the steps a little bit. Here we can see all the steps and at the end, over here, we have the code we are going to use as the main function for the Blink project. At the bottom, they may be hinting that the project will not run, and some debugging will be needed. The second document is the Launchpad User's Guide. This document's latest revision was in January 2017. In this document, we can find hardware details of the board, and at the end, we find the schematic. For this application, we are interested in the user's LED, the blue and the red LEDs, shown here in the schematic. Before we start building our project, it's a good idea to get acquainted with the directory organization set by Code Composer. So make sure you have the latest version of Code Composer Studio installed in your computer, which is the 7.1 at the moment of making this video. Then locate the TI folder in your C drive open the TI folder, go to Control Suite and open it, and from here go to Device Support and search for the device you are working with. In this case, the F28377S. Open it and select the latest version. You will see the common folder and the header folder. Open the common folder. Here the CMD folder contains command files for the linker. The include folder has common header files needed to handle the different devices of the microcontroller. And the source folder has the source code of the API files to program the hardware. Close the common folder and open the header folder. You will see again the CMD, the include, and the source folders. The CMD folder is for the linker, the include folder is to have access to the device APIs, and the source folder contains the global variable definitions. Close the header folder. We see this example folder. In this folder we see the examples of different projects that exploit the different peripherals of the microcontroller. All this is available to the developer to ease and expedite their own projects. To create a new project, we go to Code Composer Studio. Click on Project and click on New CCS Project. We type the name of the project. We select the target. We know we are working with the Delfino F28377S, and so we declare it. Now the connection. We know from the Launchpad overview document that the onboard emulator is the XDS100V2, and so we select it. Notice that the compiler has already been selected for us, which is the latest for this family of microcontrollers. Finally, we select Empty Project, click Finish, and thus we have created our Blink LED project. Now we have an empty project that we need to fill. Right-click on the Blink LED project and select Properties. Click on CCS Build. Then expand the C2000 compiler. And let's take a look at the processor options. All these options have been pre-selected for us. We see the processor version 28, the CLA support. The CLA stands for Control Law Accelerator. The CLA is an independent 32-bit floating point math processor that can be used to perform complex math operations in control loops, for example. Then we have the TMU, which stands for Trigonometric Math Unit, to assist with certain trigonometric operations. And finally, we have the VCU, which stands for Viterbi Complex Math and CRC Unit. Complex in the sense of complex numbers, and CRC for Cyclic Redundancy Check. The VCU is used for signal processing calculations, including Fast Fourier Transform, FFT. Now we go to the Include options, and we see two paths already in there. But we still need two extra paths. We click the plus icon to add them. We navigate to include the path according to our device. As explained before, this is one of the two paths we need. Here is the first path. And now we search for the second one. This is the second path for our compiler, and now we need to predefine a symbol. Let's click then on Predefine Symbols. We click in the plus icon and add the symbol CPU1. Now we turn our attention to the linker, and the first thing we need to do is to set the library and the linker command files and their path. We have here the library that is found in the Tools subdirectory. Now we search for the linker command file. Here we take the generic RAM linker command file. Another command file is needed according to the instructions, and that is found in the header folder. We delete now the original library because we are going to use the runtime library we just added instead. Now we need to add the two paths of the command files we did here. We can do it by copy and paste or by navigating the TI directory again. In any case, this is what we get. The next steps with the linker is to specify the program entry point. We open the linker advanced options and select symbol management. The new entry point is called start. With this, we have finished setting the compiler and linker, and now we proceed by getting the code files for the project. Now we need to add some files to our project, but first we need to delete this linker command file because we have already selected another one and cannot have two linker command files. Let's add the files we need. Let's click on Project and then select Add Files. We navigate through the CCS file directory as done before and go to the header directory. We select Source and choose the global variables definition file. By just looking at its name, we can figure out why we need this file. To add more files from another directory, we repeat the previous process. Navigate to the common folder and pick Source. We add several files from this folder. We add the delay file that has a function that creates a delay we can use to time how long an LED will be on. The GPIO file seems obvious since we are going to manipulate at least one GPIO. The code start branch file indicates the start of our code, which was labeled code start when we set our linker. Finally, the system control file contains important functions for system initialization. Notice that we use a link to files rather than copy files. Now we have all the files we need but one, the main one, literally. We need our main.c file. For that, we right-click on our project, select New, and from here we add a new source file, main.c. We are going to copy and paste our main file from the F28377S User's Guide document. Let's arrange this with some indents so it can look nice. Now we can build our project. For that, click on Project and click on Build Project. The project has been built successfully. It's time to load the code in the target and start debugging it. To do so, we click on the bug icon and wait while listening to some nice music. We are ready to run our code by clicking on the play icon. We click and nothing happens. There is no blinking, and before we ask for our money back, we need to debug exactly what is happening here. When we see the code, we notice that the code manipulates the GPIO 10. But if we take a look at the schematic of the launch pad, we notice that the user LEDs are the GPIO 13 for the blue and the GPIO 12 for the red one. Then we need to set up the GPIO 13 instead of the GPIO 10. Now we need to build again and load the code in the target to see what happens. We run and voila, the blue LED is blinking. However, why the red LED is on? This code does not touch the red LED, but before main runs, this LED is already on, whereas the blue LED is off. What happens before main runs needs to be investigated, but we are not going to do it here. What we would like instead is to turn off the red LED that is connected to GPIO 12. Then let's do that. We run the new code and observe that the red LED is still on. And then what happened here? Let's stop the code. The code stops in the loop. We can watch now the value of GPIO 12 is 0. It is as if the code in line 22 was never executed. This is very strange. Let's set a breakpoint at line 21. And step the code line by line to see if GPIO 12 is set to 1. That is the off condition. At the breakpoint, both LEDs are on after their initialization as output. Let's see what happens when we step the first one and it's off. And then we do the second one, the red LED, and is also off. Now we let it run to see what happens. And we see the blue LED blinking and the red LED off as we wanted. Then, running the code by itself, the red LED is not turned off with a code instruction. However, when we set a breakpoint and step the code, the red LED is turned off by the same instruction. This is very strange. Now, let's make this experiment. Let's swap the two instructions that turn off the LEDs and observe the outcome. Now the red LED is off by just swapping the instructions. Well, there is a bug here, probably a hardware bug related to some timing condition. I will inform my friends in TI to find out if anybody has seen this before, because we don't know if this is only occurs with my board. In any case, this video is just a basic demonstration on how to start building code with this launch pad. We will use this launch pad for digital signal processing and control. Stay tuned.